the workstation. A small announcement, if somebody wants to give a short talk tomorrow, I think we are planning to put some extra time for tomorrow afternoon. It's like 20-minute talks. Please let us know if somebody is interested in giving a short talk. And okay, so our first speaker is BARGHEER. He's going to say about some non-planar resummation.
Thank you very much for inviting me and for putting together this very nice program in this beautiful place. So yes, I want to talk about non-planar hexagonalization and some large N resummation. This is work with Frank Coronado and Pedro Vieira. And I'm going to start by explaining a little bit the general idea of this hexagonalization procedure. Then I will introduce a very nice correlator that allows us to go to large orders in 1/n. Then I'll explain a matrix model that helps us to compute this correlator. And I will explain some interesting limits and then conclude. Okay, so what's the idea of this hexagonalization? The idea is that correlation functions of single trace operators, local single trace operators in theories with a worldsheet description, say at large N, can be computed by decomposition into hexagons. So for example, if I have take a 4-point correlator, so I draw circles for operators on the sphere. Then this is the spherical worldsheet with 4 punctures. I cut the worldsheet between the operators, for example, in this way, so that the worldsheet is decomposed into 1, 2, 3, 4 hexagons, where each hexagon consists of 3, is bounded by 3 segments of these operator insertions. So these are some off-shell states, and 3 of these mirror states. So these are some virtual states that get inserted. And the correlator is then recovered by summing. So here on these edges, we sum over complete basis of states so this is a string worldsheet, so it's a complete basis of virtual open string states. And In practice, yes. I mean, so far I've just said very general words. So this is just the world sheet. I didn't specify. Eventually, I'll talk about n equals 4 superioring mills, so ADS. Sorry? In the case that I work on, yes, it's the beta eigenstates. And okay, so here we have a sum over these open string states, and then the hexagons are like amplitudes or form factors that measure the overlap between 3 of these off-shell physical states and 3 of these open string states or mirror states. Okay, so related to this question, the idea should perhaps work in all theories with a worldsheet description, but here I will talk about n equals 4 superioring mills or strings in ADS 5 cross S5. Okay. Now, ideally, we would like to do this thing once, perform the sum, and be done. But we are not quite there yet. Ideally, cut once, sum over these open states, and that's it. But at the level of our present understanding, it's a little bit different. So presently, what we start with is, so start with a sum over all big contractions of the free theory, of the free gauge theory, and then for each term, for each Wick contraction we then dress by such a decomposition and summation. So schematically, we have a correlator, sum of local operators, and that's a sum over big contractions in gamma, integrations over these states on the mirror lines, and a product of hexagons for each of these contractions. Right, so it should be true in general. When I get more concrete, I will just consider half BPS operators, scalar. Yeah, the hexagon might be gauge dependent, but the answer should. Yes. Okay, sorry, yes. But yeah, I'm not sure I understand the question. I mean, the contraction, of course, depends on the operators. gauge. Yeah, possible. In the sum, yeah. Individual terms, maybe. No, it's actually basically that idea. Yes. Made very concrete. So we have this. So I mean, this part is just the free theory, and then all the coupling dependence is captured by these hexagons and the mirror integrations. Right. So here's all the dependence on the coupling lambda and on the cross ratios. I mean, the non-trivial dependence on the cross ratios, say z and z bar for a 4-point function. A bit more precise. Bit more precisely, each of these wig contractions, as you all know, each wig contraction gamma has a well-defined genus G, and the prescription is to draw this wig contraction on a surface of genus G, and collect. Then we collect. In the next step, we collect all propagators that are parallel. So all parallel propagators into kind of propagator bundles. And then we cut this figure into hexagons along these propagator bundles. So for example, on the sphere, we can have a wig contraction where we have some propagators here, parallel propagators, no crossings, some here, and then some here, and for example some here. Now at the planar level this would be saturated. I cannot draw any more bundles of propagators without introducing a new handle, so increasing the genus. So that's one possible wig contraction, but of course there are others. I could not have any propagators here, but instead have propagators from here to here, like that. But I can also have wig contractions that have no propagators on some of these lines. For example, this one, propagators here and some here, maybe a few more than there, but no propagators here. So here I would naturally cut along all these propagator bundles, have a hexagon here, 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 and here. And here I have a bigger polygon, which I then need to dissect into two hexagons by introducing an artificial line. I'm just choosing to cut it along here, even though there's no propagator. I could have as well cut in this way, and the result, if this is a sensible procedure, the result should be independent of this cutting. And that can indeed be tested and verified. Yes. Well, okay, I'll make some comments about that, but for the moment, yes. This is just planar examples, but in the sum of all wig contractions, of course, I have also higher genus, And then I would draw this on a homogeneous surface and do the same. So just cut the homogeneous surface into these patches. So this is just a simple example. Okay, so given this prescription, it okay, no, let me say that later. Okay, so this is basically the idea, and we have. So this was for the planar. For the planar case, this procedure was proposed by the organizers, by Tiago and Shota. And we then later extended this to the non-planar case with João Caetano, Tiago, Shota, and Pedro. And okay, this, I mean, we could, we have tested this on several non-trivial examples, and we can reproduce the known answers and also generate some new predictions. And so this is all very nice, but there are some complications when we go to higher genus. At higher genus. So one is yes. Yes. Ah, okay, yeah, I should have said that. So for the hexagons, we have an explicit formula for all values of the coupling lambda. Yes, this is based on durability and was written by Ben, Shota, and Pedro. So it's a function of all the 6 beta states, so spin chain eigenstates on the 6 edges, and it comes in terms of the Bizet S matrix and so on. Yeah, so the hexagon doesn't know about that. No, it's a planar patch, and the higher genus information only comes through the gluing. Yes, yes, right. So here in the planar case, I had, what, 4, and then when I go to the torus, there will be more. Yes. Yes, yes, yes. Yes. So this is was very dramatic, but of course there's a 1 over n to G. K also depends on the genus, yes. Okay, so what happens at higher genus? So one thing is that at higher genus we also need to include contributions from skinny handles. So I was saying we sum over all the big contractions, and they have a definite genus, and then we insert the hexagons. But there are, of course, also higher genus contributions that are purely virtual, where I have no propagators traversing some handles, and these I also have to include. Skinny handles. So that complicates a bit. That have no propagators. Yes, yes. So then I would have a handle that is only covered by these dashed lines with no propagators. Then this sum over propagators, and this was already proposed earlier, for example, by Gopakuma also. So the sum over Wick contractions models or is an extreme limit or can be interpreted as the integration over the moduli space of on the strings theory stage. So sum over these Wick contractions is like the moduli, it's like a discretization of the moduli space. Integration. So the idea is that in the free theory, so in the string, the continuous moduli space integration in the free gauge theory discretizes on these graphs. And if we have this interpretation, then we have to, of course, mod out by the modular group, by modular transformations when we do this procedure. And that can be done, but it's a bit complicated. It acts, these modular transformations, they act straightforwardly on these free graphs, but once we insert mirror particles on these edges, so once we do have non-trivial states, it's not so clear which states, which configurations of stage map to each other under these modular transformations. So these are just some complications that arise, and we can deal with them, and we have dealt with them, but it's not so simple. Okay, so now let me go to a case where everything becomes much simpler. So now we will look at the nice correlator. Namely, we pick as one of the operators just the BPS operator, 2k fields, scalar fields x, then another state is another scalar field, also 2k, then here we have z bar k, x bar k, and again z bar k, x bar k. So then we have, so but this choice of operators makes sure that we have exactly k propagators here, k propagators here, basically k propagators on the four sides of this figure. And no, these operators cannot be contracted. They are orthogonal in internal space here also. So that's at the planar level, this would be the only contribution. And then in addition, we take the limit where this k becomes very large. So we go to the asymptotic regime. Okay, so these are half BPS. So these are half BPS highest weight operators. These are descendants, but also half BPS. As I said, at tree level, there's only this one graph. And beyond tree level, we have loop corrections. So yes. Eventually, it will be of the order square root n. Yeah, there are permutations, yes. Thank you. Yeah, so then only one or some permutations contribute. Okay. Then, so in the perturbatively, we have to sum over loop corrections within these bundles. There will be some loop corrections here, but they sum to 0 because these are BPS states. the 2-point function is protected, and so all these loop corrections within these bundles sum to 0. And then we also have loop corrections within this box, and these can be non-trivial because this is like a 4-point function, and that we know has loop corrections. So that's non-zero. Yes. Yes, so there are more propagators here. But this partial, I'm claiming that this part here alone sums to 0. I mean, these local processes here, they don't know that this is not a complete 2-point function. Yeah, at some point we will have, we will have some interactions that go all the way from here to here. But because we consider this large k limit, they are suppressed. So we only have these, and they sum to 0. Yes. Yes. Right. Okay, so this is non-zero, and all these interactions within this box we call the octagon function that has been computed by Frank to large orders. So this we more or less know. And then because of this large k limit, the interactions are basically confined to this box and to another box that is outside. But they don't talk to each other because we have so many propagators here. So this is perturbatively. In this hexagonalization picture, this is guaranteed by the fact that these mirror states on these open string lines, they come with a Boltzmann weight that goes like e to the minus k, where k is the number of propagators on this edge, times the mirror energy, and that scales as lambda to the k. So when we take k to infinity, all these non-trivial states here are suppressed, and we only have the vacuum state on each of these bundles. Okay, so this is planar. This was planar, these pictures. But I now want to argue that the same decoupling of these faces, the same decoupling persists at higher orders. At higher genus. And why is that? To see this, okay. So I was saying we sum over all these weak contractions, and they form these propagator bundles. So it's natural to separate the summation over weak contractions into a sum over all possible configurations of bundles at a given genus, and then a sum over all possible ways to distribute the propagators on all these bundles. Right? So we can fix the genus, draw some lines that represent one or more propagators, and then sum over all possible numbers of propagators on each of these edges. And this sum over configurations of propagator bundles we call a so-called skeleton graph that we then have to dress with these lengths that specify how many propagators are on each edge. So, yes. Yes. Right. It's like the BMN limit. Same scaling. Okay, so to see this, for example, at genus 1, 1, so I draw a torus. These edges are identified at my for operator. And one contribution will be a propagator bundle here, 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 and here, like in the planar case, but now I can connect this operator also here, and here, and here, and here, so I cover all cycles of the torus with these propagator bundles, and that's one contribution, which I then still have to sum over the numbers of propagators on all these edges. But when I now sum over these distributions, sum over distributions of propagators, then it's clear that all these bridges will be covered by, in the overwhelming number of cases, will be covered by many propagators. So all bundles have many propagators, as in the planar case. More precisely, when so this is a counting problem, basically. When I want to distribute, say, k propagators, I know that I have exactly k propagators between each pair of operators in total. Distribute k of these k propagators on, say, n bridges. Okay, bridges are these bundles. We also call them bridges. Between two operators. Then I have this sum over all the fillings of each of these edges, k1 to kn, such that the sum over these k1 to kn is exactly k. And when I evaluate the sum at large k, it grows like k to the n minus 1 over n minus 1 factorial plus subleading terms in k. Okay, so this will be important. And in particular, this first term does not depend or is unaffected, or only configurations that have a large number of propagators everywhere contribute to this leading term. So for large k, this means that the answer, the sum over big contractions, will be a polynomial. In k, that such that at fixed genus there is all contributions come from graphs, only graphs with a maximal number of edges. Because I have a maximal number of these bundles. Because when I have fewer than maximal bundles, I will have fewer powers of k from this sum, and that will be suppressed when I only look at the leading term in k, say. So leading order in k. And also, as I said, all the bridges carry a large number of propagators. So again, all the loop corrections are confined to these individual phases, and the phases don't talk to each other because they are just so separated. So then the answer will also be a polynomial in this phase, in the octagon. clear? Yes, because we choose the polarization such that there are no propagators here. So this two hexagons are glued into an octagon, and that happens in all the faces of the graphs. So we have a quadrangulation of the surface. We sum over quadrangulations. Okay, so yes. Yeah, so in ADS, the picture is, these are some heavy BMN states, so they map to heavy geodesics. And then these faces will span some surface between these geodesics, but they will not backreact on the geodesics. So I have my 4 points on the boundary, and then I have geodesics. And some surface here that spans between these geodesics. Yes, in the planar case, right, there are 2 copies of this thing, so yeah, so there are, yes. At genus 1, several things can happen. There are several contributions at genus 1. The most simple is just the one where I have no surface here. So just these BMN strings, then there's a handle here. That's one, but there are others. I can also have yeah, I mean, yeah. So, yes. Well, okay, it will become, yeah. So there are, yeah, I mean, they are just differently connected, these geodesics. There are some faces that have I mean, there are some faces in these graphs, but they have no extent in ADS. They just go along these lines and connect. I mean, they have some. Yes. Yeah, then they. Yes. So that's one contribution, but there are also others where I have. Yes. Yes. Yeah, so this has no area, of course. But I can also have basically 2 copies of this glued together. So how do I draw this? This is still one geodesic. I just open it a bit just to show what's happening here also. So then I have 1 copy or 2 copies of this surface connecting this with this, with this, with this, and another 2 copies connecting this with this, with this, with this. So, okay, that's impossible to draw for me. But now the handle is here, so it goes here. Right? Okay. Okay, so yeah, so here I still have surfaces. I just haven't drawn them, like here. So that, of course, has area. This does not. That can happen. Yes, yes. That can happen in Lorentzian signature, I guess. In Euclidean also? Yeah, okay. Yeah. Yeah, yeah, right. Thank you. Right, there's one more. Okay, so this was planar. This is genus 1, and then genus 1, there's another one. Where I just... Did you mean this one? So again, I have just 2 copies on top of each other. And then a handle here. Is that what you meant? So this is another. Ah, yes, okay, okay, but that is suppressed. You mean a handle here? Like, okay, yes. But this would be one of these skinny handles that has no propagators. So it's suppressed in this large K limit. If we look at leading term in this large K, it's suppressed. Yes. Okay. Okay, so now, as I explained, the answer is a polynomial in this octagon. The octagon is like this surface that I drew. I mean, yeah, not locally. I mean, no, only this, yeah. The handles are always, they always open on these geodesics, not inside the surface. Okay, so this octagon will be explained by in Frank's talk. But it is this function from the gauge theory point of view that lives in this box. And so now at genus 1, I drew the examples here in ADS. If I draw them, so they already show that I can have like 0 copies of this octagon here. I can have 2 copies here, like in the planar case, and here I would have 4 copies. Each surface has one on the top, one on the bottom. And so in terms of these graphs, it would be, I could have this graph that I drew before. That has one octagon here, another octagon here, another one here, and another one here. So this has 4 powers of the octagon. So that would be this surface here. But I also have other terms. I can have other Wick contractions where, for example, this edge is, so then I have this edge would go this way. And yeah, what am I missing? Ah, okay, sorry, yes. Good. So I wanted, okay, let me flip to not get confused this edge. So it goes here, here, here. Now it's okay. So now I have, again, an octagon here, an octagon here, and here I have also octagons, but they only see 3 of the operators. So this octagon here, this, but not this. And the other octagon sees this, and this, but not that. So these octagons only see 3 BPS operators, and therefore they are protected. So all the coupling comes from these octagons, which we called, which are again copies of this O. And then if I would also flip this bridge, for example, then all the octagons would only see 3 operators, and then I would have O to the 0. So I can have these types of contributions, say a genus 1. And these map to these different contributions there. And at higher genus, it's similar. So I can have graphs with 0 of these non-trivial octagons, 2 powers, 4 powers, 6 powers, and so on. It's always an even number of powers, which one can see by consistency of the graph. Because they only see 3 BPS operators. So they are like 3-point functions of BPS operators. Okay. So that explains why we have a polynomial in this octagon. So the end result is, okay, what are the phases? The phases are this octagon that I showed before. So I have operators 1, 2, 3, 4. This is non-trivial function of the coupling. Then I have these other octagons. So because propagators can only connect adjacent operators, so 1 can only talk to 2 and to 4, but not to 3, I can also form these other octagons that I just mentioned, which would be, for example, this. 1 talks to 2, 2 to 3, 3 again to 2, and 2 to 1. And because, as I said, these are just 3 BPS operators, so this is just 1. We call it BPS octagon. Or I could have something like 1, 2, 1, 2. So this only sees 2 BPS operators. Call this O prime, O. And that's also protected. So I have these 3 types of faces, and only this is non-trivial. And because I have only octagons, we can use the Euler formula to find the number of octagons. So 2g minus 2 is the number of vertices, which is 4 operators, plus the number of faces, which is, say, n, minus the number of edges, which is the number of faces times 4, because they have 4 edges, divided by 2, because every edge is shared by 2 faces. So that's 4 minus n. So we have n is 2g plus 2 octagons at genus G. So we have these quadratizations of 2g plus 2 squares. Okay, so in the end, the correlator that we want to compute plus n minus, okay, this is n. 4 plus n minus 2n. Ah, okay, sorry. Yes, good. No, that's not true. Okay, where's the mistake? Overall minus where? Here. Ah, no, that doesn't make sense. Ah, no, it does. Oh, wait, no. Yes, thank you. Okay, good. So the correlator normalized by the free correlator at lambda 0, genus 0 is, as we saw, the first term is the planar term, which is just octagon squared. Then we have k to the 4 over n squared. Because this k to the 4 comes from, so we have 2g plus 2 squares, so the number of edges is 4g plus 4. So we have, for each genus, we get 4 more edges. And because of this combinatorial factor, from distributing the propagators, I get 1 power of k for each edge. So going from genus 0 to genus 1 gives me 4 powers of k. And then I have a polynomial of degree 2 in the octagon, whose coefficient, or in the octagon squared, whose coefficients are just numbers. And then at genus 2, I have k to the 8, and 4 polynomial of degree 3, again in octagon squared, and so on. So this we define as our function of interest, A, that depends on zeta. Zeta is rescale k, so we rescale k by square root n. Yes, and then this is just a function of this zeta, and the octagon, that is purely combinatorial. So all the coupling sits in the octagon, and yeah. So besides these powers and the octagon, it's just numbers in this expansion. Okay, so so now all we need to do is compute these polynomials and the octagon. So the octagon will be explained by Frank. So we want these polynomials. And there are several ways to do this. So the polynomials are basically these polynomials, g plus 1. They count graphs. They count graphs keeping track of the number of octagons in each graph. So each coefficient is the coefficient of O of the octagon to, say, 2n is the number of graphs that has 2n copies of this non-trivial octagon. Okay, so one way to do this is by brute force. We can just construct all these graphs at a given genus and count them. Enumerate, look for the octagons and count the graphs. So we did that up to genus 3, and then in total we find 6 graphs at genus 0, 215 graphs. Sorry. 6 graphs at genus 1. Genus 0 was just 1 graph. 215 graphs at genus 2, and 26,779 graphs at genus 1, 2, and 3. So the number of graphs grows very quickly, and it's very inefficient to construct them all because we only want to count them. Right? We don't need the local details of all these graphs. So what do we do to count graphs? That's one prime purpose of matrix models. Okay, I have to shortcut this. But we basically can convert the problem to a matrix model that counts these graphs for us. Where now, so this counts the dual graphs. So in this matrix model, each of these faces that we have, the non-trivial and the BPS faces, is one 4-point vertex. Then for each type of edge, we have one edge from 1 to 2, one from 2 to 3, one from 3 to 4, and one from 4 to 1. So these are 4 modeled by 4 complex matrices. So we have matrices A, B, C, D, and vertices for these types of faces. And I can write yes. Well, yeah, I mean, in this large K limit, we don't keep all the contractions. No, then still we get, yeah, I mean, we have, yeah, right, we have to, yeah. Yes. Okay, so, right, so now partition function of this matrix model is integral A, B, C, D, kinetic term, interaction term, and the interaction term is all these faces. So we have an octagon. That's just a coefficient in this matrix model that counts, counting coefficient. So we have trace A, B, C, D. That's the non-trivial octagon that goes from 1, 2, 3 to 4. Then we have the reversed octagon. That's A bar, D bar, C bar, B bar. And then we have the BPS faces, which are trace A bar would be the face that goes 1, 2, 1, 2, 1 squared, plus the same for B, C, and D. Plus then we have the other BPS octagons that see 3 operators. So for example, A, B, B bar, A bar. No, this doesn't come yet. Plus the cyclic copies. So this coefficient makes sure that we count the number of octagons within each graph. And then we have the kinetic term, which is just trace A bar. And here we introduce another counting factor, B bar. And these counting factors make sure that we know for each graph how many edges of which type we have. So that each graph will come with a certain power of K1, K2, K3, K4, and that tells us how many edges do I have from going from 1 to 2, from 2 to 3, and so on. So these are very important because the matrix model counts the graphs, but we then have to supplement these graphs by this combinatorial factor. So to get the numbers that we want, we have to okay, so this will now have this will have many terms, this partition function, but we only want the terms that have four faces, because in the dual graph each face is an operator insertion, so we want 4 faces. We only are only interested in the term n to the 4. But this n is now the rank of these ABCD matrices, is not the NC of Young-Mills. So 4 faces. And also, we want only graphs that include all types of connections, because we know that there have to be k propagators between all the pairs of operators. So we want terms that include at least one power of this k. And then there will be a coefficient that we define to be curly z. And that is now a sum over the genus and some polynomial p tilde for g plus 1. That is a polynomial in all these ki and the octagon. So this is degree 4g, homogeneous degree 4g in the ki and degree g plus 1 in the octagon. And these are not quite the polynomials that I wrote somewhere there. We get those polynomials by adding these. We still have to add these combinatorial factors. So when we expand this thing, then we have to supplement to get our polynomials of degree for g plus 1. We have to take these polynomials and expand and then replace every power of this k with the same power divided by n factorial. Okay, I'm at 0. That's not so good. Okay, so let me maybe just okay, what should I do? Okay, so now we basically need to solve this matrix model. We cannot do it in general, but we can do it in some limits. No, do I have 5 minutes to? Okay. So we would like to solve this in general, but that's a bit too complicated so far. But obviously there are some interesting limits that we can look at. So one limit is limits. We can look at obviously the limit where the octagon goes to 1, so that's the free case. Then we can look at the octagon going to 0, and we can look at the octagon going to infinity. Okay, so this case, a bit embarrassingly, we have not managed to compute the free octagon. What we could compute is these two cases, where the octagon becomes either 0 or infinity. So when the octagon goes to 0, it's a very non-perturbative case, because in the free theory, the octagon is 1. In this limit, it goes to 0. So the loop corrections have to cancel, have to combine, and have to cancel the full tree result for this octagon. And in that case, we only have the BPS squares. We only count graphs with these BPS squares. And that's very similar to extremal correlators. Similar extremal correlators, which also only have these types of squares, and they become products of sinh functions. So we made an ansatz of these sinh functions, and we could match it to the data that we found from the matrix model. and we find that this correlator of Z and the octagon is just sinh 3 half zeta octagon squared over 3 half zeta octagon squared to the power 4. So this is for all the answer for all genus in this case. Sorry, that doesn't make sense, right? There's no octagon here. Thank you. Okay. Good. So the other case, let me just flash it. Here we have only this octagon. We discard all graphs that have these squares. That simplifies the combinatorial problem a lot. It basically reduces to a single matrix model, a matrix model with a single matrix, and that we can compute basically by character expansion. And then we find that this correlator is there's some, okay, it's basically octagon squared. Sorry, so 1 over. So here I keep these several different. Oh no, okay, so zeta 4, 1 over zeta 4 times the sum over genus some omega to the g plus 1. This omega is basically octagon squared weighted by the zetas. So g plus 1 squared, g factorial squared times another sum to g m factorial squared 3 minus m factorial squared. But this omega is zeta to the 4 octagon squared. And this we can resum, and it becomes octagon squared, some double integral over Bessel functions. So there's st, s plus t plus 1, I naught 2 st omega minus 1 minus s 1 minus t s plus t plus 1 I naught I could make some more comments, but I think I should stop here. Yes. Yeah, so these limits could both be relevant for a strong coupling. So this limit would be, for example, yeah, the ones that these graphs that I showed that have no surface. So this limit would count those configurations, and in a limit where the surface becomes big, those configurations would be suppressed and only these would survive. The other limit, as Fernando said, could also play a role. For example, when we continue to Lorentzian signature, it could become infinite, the area. Sorry, negative. Okay, I'll just stop because I'm out of time.